In the previous section, we studied homogeneous linear second-order differential equations of the form ay double prime plus by prime plus cy equals 0. Each of these equations has a corresponding auxiliary equation, ar squared plus br plus c equals 0. Based on the solutions of the auxiliary equations, we reach the following two conclusions. If the auxiliary equation 2 has two distinct real roots r1 and r2, then y of t equals c1 e to the power r1t plus c2 e to the power r2t is the general solution to the differential equation 1. If the auxiliary equation 2 has one repeated real root r, then y of t equals c1 e to the power rt plus c2t times e to the power rt is the general solution to the differential equation 1. So what if the auxiliary equation has two complex roots, r1 equals alpha plus I beta and r2 equals alpha minus I beta? Is y1 of t equals e to the power r1t equals e to the power alpha plus I beta t still a solution to the differential equation? And if so, how do we interpret this? We're going to use Euler's formula to figure this out. And Euler's formula says that e to the power I theta can be written as cosine of theta plus I times sine of theta. We can then use that formula to rewrite e to the power r1t, which is equal to e to the power alpha plus I beta t. And I'm going to distribute the t here, so I get alpha t plus I beta t. And then I'm going to use a property for exponents, and I'm going to write this as a product of e to the power alpha t plus, or times e to the power I beta t. So I'm going to keep that first part, e to the power alpha t, but now I can rewrite e to the power I beta t with Euler's formula. So what I need to do is I have I beta t here and I have I theta here. So the beta t is going to play the role of theta. So I have cosine of beta t plus I times sine of beta t. And I can distribute that e to the power alpha t then, and I get e to the power alpha t cosine beta t plus I e to the power alpha t sine beta t. Now, one can show that these complex valued solutions actually give rise to real valued solutions as follows. So if the auxiliary equation has complex conjugate roots alpha plus or minus I beta, then two linearly independent solutions to the differential equation 1 are e to the power alpha t cosine beta t, so that's the real part here, and then e to the power alpha t sine beta t, that's the imaginary part here of the complex solution. And a general solution is then given by y of t equals c1 e to the power alpha t cosine beta t plus c2 e to the power alpha t sine beta t, where c1 and c2 are arbitrary constants.